Is I don't know, a lot of review really. We already went over this equation y equals a times b to the x in chapter 5, so this goes into it a little bit more in depthly, but it shouldn't be too big of a stretch if you already feel comfortable with the equation y equals a times b to the x. So we're going to just start with b to the x. You'll notice we ignore the a at the beginning of chapter 8. So in this lesson, you'll investigate the characteristics of the family of functions y equals b to the x. As a team, you'll generate data for various functions in this family, form questions about your data, and answer each of these questions using multiple representations. Your team will show you what you have learned on a poster. So beginning to investigate exponentials. You already know the equations of the form y equals mx plus b represent the family of linear functions, and you know what effect changing the parameters m and b have on the graph. Today you will begin to learn more about the exponential function family. In their simplest form, the equations of exponential functions look like y equals b to the x. In chapter 5, you graph several exponential functions. Some graphs, like those that modeled the rabbit populations, were increasing exponential functions, like those two, and look similar to these two at the right. Others, such as the rebound height graphs from the bouncing ball activity, represented decreasing exponential functions and look similar to the curve shown in bold at right. So that was this one that went down. Each team member should write down 3 different numbers, use these numbers as values of b, and use them to write 3 equations of y equals b to the x form. Graph your equations using your graphing calculator. Compare your graphs with your team. Are the graphs similar? Did any of the graphs appear to match the ones above? So I'm going to kind of put 8.1 and 8.2 together. So 8.2, it says each graph your team created in the previous problem probably looked different from the others. How many different ways can you graph y equals b to the x? So what I've done is I've gone into Desmos and I put an equation y equals a to the x. I guess I could have, actually, I didn't even think about this. I could have put a b just as easily, and it would have been what we have there. So y equals b to the x, and you'll notice as I change that b, I just have a slider here. The higher it goes, the steeper my curve is going to get. And as it gets closer to 0, you'll see it begins to flatten out until when it gets to exactly 1, you'll notice that it's actually completely flat and a flat line. So even though it's a curved equation, we actually get a flat line. Now, hopefully you recall this from chapter 5, but anything between 0 and 1, it begins to go down. So it's gonna curve down, and again, the further it gets, the steeper it's going to get. Finally, when I get to 0, you'll notice, I don't know if you can see there, but there's just sort of that half line right there. It starts at 0 and it goes to the positive. The domain doesn't allow a negative, so there's no x's there in the negative. You just can't get an output that's negative. And then finally, it kind of breaks if I go to negative. And it doesn't really show here, but if I had a negative, what would be happening is it would be going back and forth from a positive to a negative. So that's why it's not really appearing there. So that kind of answers some of the questions of what happens to the b as it gets positive and negative in between 0 and 1 and all those types of questions. There we go. So that kind of lends to problem 8.3. The graph of the function y equals 1/2 x is shown at right, and we already did that in Desmos. We noticed that it opened down. So describe what happens to y as x gets larger and larger. So what is y when x equals 20? Well, think about it. What's going to happen here is as I put in x's, so if I have y, if I have y equals 1/2 to the second power, that's like saying y equals 1/2 times 1/2, and I get y equals 1/4. That went really well. So if I have y equals 1/2 to the 4th power, That's like saying y equals 1 half times 1 half times 1 half times 1 half. If I multiply the tops, 1 times 1 times 1 times 1 is 1, 2, 4, 8, 16. So here I have 1/4, and here I have 1/16. So the more I add to the x, the smaller the y gets, which makes sense because it's going down. But you'll notice I'm always going to have a 1 on top, right? If I multiply 1 half a billion times, it's going to be 1/2 to the billionth power. But it will never get to 0. And that's really what the book is trying to get you to understand, is that there's something called, and hopefully you remember the name, an asymptote. And what that asymptote means is that you're never going to get to 0. This gets closer and closer and closer, but it never touches that x-axis. So that's what happens there. So when c is very large, the graph y equals 1 half to the x approaches the x-axis. That is, as x gets larger and larger further along the right, so the further it gets over here, the curve gets closer to the x-axis. In this situation, the x-axis is called an asymptote. You can read more about asymptotes in the math notes. And so does y equals 1 half x have a vertical asymptote in this direction? The answer would actually be no. Even though it looks like it stretches more and more, I'm able to plug in like -1 billion and -1 trillion. It would just be super, super steep, obviously. But there is no asymptote vertically, only horizontally. And again, hopefully that makes sense because you can plug any value you want in for x. The domain isn't limited. I could plug anything I want. But as far as output, I won't get 0 or anything below it. So the range is limited. So investigations. It says, now that you, with your class, have found out all the possible values for graphs y equals b to the x, your teacher will assign your team 1 or 2 of the graphs, types of graphs to investigate further, completely describe the graph. So, may jump over to Desmos and just sort of as a thought exercise, if I had given you 5 to the x, you would say it opens up and it's fairly steep. If I had given you 2 to the x, you would say, it's more flat, but the closer I get to 1, the flatter it becomes until I get between 0 and 1, and then it actually opens down. So just to kind of reiterate all those points that we've already discussed is really what 8.4 is asking us to do. 8.5, exponential functions have some interesting characteristics. Consider functions of the form y equals b to the x as you discuss the equations below. Exponential functions such as y equals b to the x are defined for only b is greater than 0. Why do you think this is? Well, again, when we had b equals exactly 0, we just got that weird half line, and when it was negative, it disappeared completely. So that would be why we would say we want to limit it where b is going to be positive to some extent. That way we can either get a downhill curve or an uphill curve. And can you consider y equals 1 to the x or y equals 0 to the x to be exponential functions? I personally would say yes. I mean, there's still that kind of equation. We don't get that curved shape, but to me, that's just part of a caveat of an exponential function. I think the book disagrees with me on that, and they say that they're not really considered exponential functions because we don't get the curve. So whatever. I mean, it is what it is, but hopefully we feel pretty comfortable with those curves. Have a good one.